Okay, so hi, I'm David Duvenaud, formerly a Ph.D. student at the Computational and Biological Learning Lab. I finished in 2014, back when the lab was still all vision non-parametrics all the time. And I guess, we've all moved on to deep learning a little bit. I'm really excited to talk. Oh yeah, this talk, I really want it to be interactive. And I think this is the perfect audience for this talk, which is me talking about a newly practical generative model that I think is non-parametric in a sense that you guys will appreciate. And I'm going to talk a little bit about the relationship between this model class, between Gaussian processes and neural processes. But I also want you guys to help me flesh out these relations, because there's a lot of open questions. All right, without further ado, so let's jump in. Okay, so just for anyone, here's the main takeaways that I'm going to tell you about is this new model class, latent stochastic differential equations. And they are a standard generative model class. Every query is well defined. So unlike neural processes, but like Gaussian processes, and they can handle arbitrary dynamics and likelihoods. So I'm going to talk about how later this can handle data that is like doctor's notes written at different times, right? As long as I have a little language model. The main technical meat of this talk is going to be saying how do we get gradients of marginal likelihood for these stochastic differential equations. And we have a nice asymptotically zero variance gradient estimator, which might sound too good to be true, but it is true under some conditions, you'll see. And then basically, we're just starting to explore this model class, and it's wide open, and I would love to collaborate with any of you in this area. Okay, so I think some of you guys might have seen like the first part of this talk before. The motivation for all this continuous time work was from a real problem that one of my students, Yulia, or rather Craig Morse's student that I was working with, Yulia was handling, which had irregularly sampled data through time. And it was like tumor assays, but most real business data and real medical data is like, here's the time and here's these different types of measurements that someone could have made about a patient or a business or a tumor or whatever. And so here is like an actual data set of a single patient in an ICU over 48 hours. And all these different doctors and nurses are measuring his like blood pressure or temperature or whatever at different times. And we don't see the measurements here, just the measurement times. And so I still think this is like a giant blind spot in machine learning in general, is that, about half the practitioners that I talk to say, yeah, I'm like, want to use deep learning, but my data doesn't look like a giant, pair of examples. It looks like this horrible, messy sort of like user traces. And we definitely don't want to bin the data. That should violate the statistician's oath. I think, in the spirit of automating machine learning, I really want to push our models as close to the raw sensors as possible. So one way of viewing all of this is to answer the question, how do we make our models natively continuous time so that they can handle continuous time data without any sort of manual pre-processing? Okay, and then just to get you guys on the same page notationally, the sort of bread and butter of continuous time models is differential equations. And in that setting, we have some vector valued state that represents our system, like, the health of a patient or the position and velocity of some planets or chemical concentrations. We define the instantaneous change of that state with respect to time by some function, and that function can be some neural network. The point is it depends on the current state and maybe time. So it defines some sort of gradient field. And then usually when we want to make predictions in this type of model, we have to solve some initial value problem where we know what the position is at some point, and we have to solve this integral, which involves finding a trajectory that matches this vector field. And a lot of the work in this area uses Euler's method, which is a good, I think, theoretical tool that says, we can approximate these trajectories by starting at some point, taking a step in the direction of the vector field, and then continuing this. But it's a terrible ODE solver. And if you have to choose your discretization before you even run your model, I would say that's like a very important hyperparameter that I'd say can and should be chosen adaptively. And there exists adaptive solvers for both ordinary differential equations and stochastic differential equations that can take steps according to how complex the dynamics are. And you just specify the error that you want, and it usually roughly matches that the error that you ask for. I mean, that's a much better way of parameterizing the trade-off between speed and accuracy, is to let it be determined on the fly. Okay, so everything we do in this whole talk is going to be done exactly in continuous time. And then only at the very last minute are we going to send it to an adaptive solver who's going to choose the discretization on the fly. Okay, so I want to not skip over the simplest and sort of dumb but effective way of dealing with continuous time that everyone should try first as a baseline, right? Like, we're going to get fancy for the sake of fancy a little bit later, but if you actually have data like this, the first thing you should probably do is take a recurrent neural network and just feed the data to it. So the idea is that in a recurrent neural network, there's some vector h, which was like the current hidden activations. We have some function, some stateless function, we call it RNN-cell, that takes the current state and the current data point and updates it. So this is a little figure showing that, like, maybe these are the different activations of units. They see a new data point at this time, they get updated. You can also tell it what the time delta was from the previous observation. And then in principle, you have a consistent model. Like, this RNN sees all the information that it in principle needs, and with a rich enough neural network here, it could learn any, to make any sort of predictions or characterizations of the data set that you want. And the main point is, this is simple and fast, and you should try it first, because it might, if it works, you're done. The very first way we can start to sort of improve on this is this ODE RNN, which takes into account the fact that not seeing an observation is often informative about a system, right? So I like to use the example, it's like, what if I'm waiting for a bus stop for my friend? So maybe at this time I, talk to them on the phone, then I show up at the bus stop and I see that they're not there. Then as I'm waiting, I'm actually gaining evidence about what's going on with my friend instantaneously. So my beliefs should be updating instantaneously. And these H's, the hidden state in the neural network, represents like a belief state. So a very simple hack we can do to make things sort of like more natively continuous time is update the hidden units in between observations with an ODE. And again, this is just deep learning engineering. There's no like real, I think, strong claims I can make about this model class, just that I think factors things a little bit more nicely. Still a hack, still something that's simpler than what I'm going to be showing you in a minute with latent variable models. Okay, any questions so far? Anyone just want to say hi? I'm really happy to see all these names, at least, that represent people that I adore. Okay.
Hi, David.
Yes. Oh, Hung. Yes.
Hi. I just wonder, in general, is it okay to replace this ODE solver with a latent dynamic model if we know the dynamics?
Oh, yeah. So, yes, but then you have to do inference. So that's a great question. And that actually leads it right into this next slide, which is that I think this is something that this CBL will understand, is that RNNs are not latent variable models, and the H is not, the state of our system. It's some sort of like scrambled belief state about the true state of the system Z. And so it's not really a well-defined generative model. If we knew the dynamics, it's not clear how we could stick them into this RNN. And also, this RNN has to learn a lot. It basically has to learn Bayes' rule. So even if I knew the likelihood, this RNN would have to learn how to incorporate new data from scratch. So that's good when we don't have a good model. When we think we're going to have terrible model misspecification, then we should learn to do inference from scratch. But if we do think we have good dynamics and unlikelihood, like maybe it's a physical model, it's kind of pointless to ask the RNN to relearn Bayes' rule, and that it's not going to generalize as well. So, but I think that's like, you guys will be very sympathetic, of course, that to the benefits of latent variable models over just, black box neural networks. Okay, so yeah, so the whole direction I want to move in is to do something that looks more like a hidden Markov model or a Kalman filter, or it was sometimes called deep Kalman filters, where you have nonlinear transitions and nonlinear likelihoods, or like non-Gaussian likelihoods. They've been sort of rebranded as deep Markov models. But I think this is like an awesome model class, and it's like even still today like underappreciated, although I guess you guys would really appreciate it. Yeah, so, and then the only problem is we have to do inference, but we can just learn a recognition network or do whatever. It's so nice to be able to skip over this part with this audience. Okay, so how are we going to build a continuous time deep Markov model? That's sort of like the next part of this talk. So the next thing we could do is to say, okay, well, let's say that there's some latent initial state Z, T0. That's like, what is the state of my business on day one, or the state of my patient or whatever. And then say that the dynamics of that state evolves deterministically according to some ODE. And then I get to see some, noisy observations according to some likelihood. So this is good. This natively fits that data set that I showed before, because I can handle data points at arbitrary times. And now it's a generative model, so it has well-defined answers to any query you might ask. And just to show what learning in this model looks like, here's a very simple toy example of, so here's data, sort of like a sine wave, like a noisy sine wave, a few different trajectories. They're missing lots of data points. The parameters in this model are the likelihood, like what is the noise on these data points, and the dynamics, which is like what is that F function saying how these trajectories move in the latent space. So this block down here is showing what that, at initialization, what that F function looks like. And now I'm just going to jointly train everything as a variational autoencoder. And this is I think we use the 4-dimensional latent space in this example. And so this is just a 2-dimensional slice, but it learns, that roughly these, it learns a sort of periodic trajectory. So this is just the magic of VAEs. You guys are all familiar with this. The point is, there's no more special technology we need once we have ODE solvers in our like PyTorch or whatever. We can just define our model to include those ODE solves and jointly train everything with gradients. Right? All right. Any questions so far?
I have one question, David. Could you give some? I mean, some key thing in variational autoencoders is this inference network or the approximate posterior distribution. Could you give some details on what it is?
Yeah, great question. So that's kind of awkward, right? Because so in this setting we have to get a approximate posterior over Z given all the X's. So we have to somehow slurp up all this data. And so that's where we used ODE RNNs for that. Or in the first paper, we just used RNN, and then in the second follow-up paper, we used an ODE RNN. I mean, again, we just need to design a function that takes in a arbitrary time series and outputs a vector. So that's just like a question of like deep learning gluing things together. There's no theory, I think, that we can say here. There's no like order invariance, or I can't think of any invariances that we would want to encode in that encoder architecture. So I didn't really think too hard about it. I just wanted something that had at least the right type and didn't have to bin the data. I think Patrick Teacher has some interesting variations recently where he tries to make some sort of like local encoder that sort of fits a spline to the data, but that's very specific to when you have like continuous data with like, little small amounts of noise. I'm interested in the very general setting where these, again, are like crazy language models or image models or who knows what, and you can't fit splines to anything. Any other, does that answer your question, Miguel?
Yeah, thanks.
Okay, cool. So yeah, so we fit this thing to, I was saying it fits this data. And so just to show that this basically works, so we started off with like our baselines, and those RNN where you just look up the data. This is like the unprincipled, fast, hacky thing. It kind of works. ODE RNN helped a little bit. That's still hacky. Then the latent variable models, the latent ODE did best. Great. Okay. There's one thing that didn't help in this setting, but I think is really cool, and you guys will appreciate this latent ODE plus Poisson. So we can actually, once we have ODE solvers in our like differentiable, machine learning packages, we can have arbitrary Poisson process likelihoods where you don't have to make things like be like exponentially decaying or anything. So this lets you condition on the timing of the observations. And those are usually, actually in many settings, those are really informative. Like imagine if I showed you two people's medical records and I erased all the results of all the tests. So all you see is like on this day, this person got this test. And so maybe one person has like a yearly doctor's checkup and you're just like, well, they're probably pretty healthy. And then the next one is like yearly checkups until suddenly all sorts of tests. you're like, oh man, something's going on with this other guy. So without even knowing any of the results of the tests. So we often want a condition on that. And now we can, the Poisson process likelihood, it involves an integral, a one-dimensional integral over time. We can make that the rate depend on the current state of the patient. And so this is just, anyway, something that we can code up and take ratings with respect to, no problem. And so in this simple example, we actually were learning a pretty good model of, here's like our posterior Poisson rates over when people were going to measure the blood pressure of a particular patient or their oxygen level. And so it's saying like, oh, when they enter the hospital, they're going to get their blood pressure taken a lot, and then not so much later on, right? So point is, Poisson processes, you used to have to write down like very specific forms where the integrals had closed form. Now you don't. You can just have whatever you want and just roll up your sleeves and do the integral. Okay, so now this is the end of the like straw model class. I'm saying this is a weird model class because it's deterministic. And so it basically means that we can be uncertain about the initial state of our patient or whatever, but then once we know that initial state, there's sort of this clockwork mechanism that's going to evolve deterministically. And so if they get hit by a car like a year later or something, that has to be somehow like encoded into this initial state, like where they were fated to have whatever happened to them. And so that means that the more data I want to model, the more stuff I have to stick into this state. It's not very natural. And we want to be able to incorporate the fact that there's going to be all sorts of unseen interventions on our state that we don't get to directly observe. You can do that with the sort of like jump processes if you want, but and that's a good direction, but I'm going to try to go a slightly different direction from here. Okay, so before we get into SDEs, any last questions about this part? Cool. Okay, so I mentioned before that I really want to make a continuous time version of this deep Markov model. And it has stochastic transition dynamics. Not necessarily in the sense that we're uncertain about the dynamics, but rather that, you know, this is a little probabilistic graphical model, and there's a distribution of, you know, Z2 even condition on Z1. So one way to, like one sort of cartoon version of writing down noisy transition dynamics is to say our new latent state is our old latent state plus some deterministic change plus some noise. Okay, so if we had this set up, now the next thing would be to make these, the timing, like the time delta is smaller and smaller. So how can we make this more continuous? Well, we could like, sorry, one second. We could sort of, you know, add an extra Z1.5 in between all these and keep subdividing these transition dynamics. And of course, the beautiful thing about this being a generative model is that we can ignore, like if there's a time step where there's no observation, that's fine. We can integrate out the unseen observations in closed form. It's the likelihood integrates to 1, so we just leave it off. So there's no reason we can't just take the infinitesimal limit of smaller and smaller transitions. And what do we get when we do that? We get stochastic differential equations. And this is the classic thing that people have been, you know, doing theory about and using in finance for like 70 years. I need to mention that because there was a few papers that came out in the last few years where someone said, I'm going to take an ODE and add like noise to the solver or some thing that didn't have sensible limits. So I'm not trying to reinvent anything. This is exactly the standard SDE thing that you'll find like all these crusty old textbooks about. And so when I first started learning about these, I thought they seemed pretty intimidating. They have like weird integrals and stuff. There's only one really funny thing about them is how they parameterize the noise, or how they write down the noise. And so I'll just show you that guys right now, and it's not actually that weird. Okay, so I said we want to have an SDE, or we want to have an ODE, but with noise at every, like instantaneous noise. So the question is just how do we have noise that's instantaneous, that's not either like 0 or infinite when we take our limits? And so the way that you can do this is to say, okay, the change in the state is the deterministic part times the change in time. So that's just the same as we had before. That's just an ODE. And then we have this other function that scales the amount of noise. And this dBt, that's our Gaussian noise. And B stands for Brownian motion, and dB just means we take our two different time points in our Brownian motion and subtract them. And so this will be marginally Gaussian, and it'll shrink as we shrink dt. So it's weird. We take white noise, we integrate it to get Brownian noise, and then we take finite differences to get back some finitely sized Gaussian noise. Anyway, so one thing to note is that this kind of looks like a little Gaussian, where we say, oh, we have the mean here, and then we scale the variance by this, or we scale the noise by this standard deviation. So this is cool because now this is putting an implicit distribution over functions, just like a GP. As soon as I write down an initial state of Z0 and write down one of these functions, now marginalizing over the Brownian motion gives me a whole joint distribution over functions, again, like all the things we're used to playing around with. And so this is a little spoiler, but here is a SDE that has been fit to this data. And these gray lines are showing the drift function. So they're kind of corralling these trajectories to go near the data. And then there's also a diffusion function, which is fixed, and it's just adding noise at all the points. And so these purple lines are samples from this a particular SDE with this drift function and a unit diffusion function. Okay, any questions so far?
Can I just ask a clarifying question about the Brownian noise? Would it be accurate to say that this is equivalent to taking a random draw of Brownian noise and then essentially integrating that deterministically with this dBt sort of already defined, just like a multiplying factor?
Yeah, I'm so glad you asked that. So yes, it is. So the way I like to think about this, and it's not how it's normally thought of though in the SDE literature, but yeah, if I wanted to sample a trajectory, I first sample an entire Brownian motion trajectory, then I do a deterministic integral. Yeah, you kind of spoiled the main technical contribution almost of this talk. Awesome. And so one thing is this, I want to just talk about what are SDEs appropriate for, because they seem pretty restricted. It's oh, okay, you're using Gaussian noise. That seems maybe that's just one special class. They're actually more flexible than they seem. So the first Brownian motion is named after Brown, who was this guy who looked at dead pollen cells under a microscope and saw that they were still moving around. And he said, that's weird, they're dead. And then Einstein, his first major contribution was to say, it's actually little unseen interactions, millions of them per second, of water molecules hitting these pollen cells. But it doesn't have to be Gaussian. The interactions, again, don't have to be Gaussian. They can be discrete things, like when two animals have a baby or one of them dies or whatever, their allele frequencies go up and down by a discrete jump, or prices in the market move a little bit when people learn something. The central limit theorem is what's making what's making this noise Gaussian instantaneously. So when you take the limit of all sorts of different instantaneous interactions, you either end up with you have to either end up with something deterministic, or a jump process, or Brownian motion. It's sort of only those three things. Okay, so it's 2021. Let's stick some neural networks in the drift function and diffusion function and fit this to data. Okay, so the next part of this talk is just going to be, how do we get gradients? How do we define a sensible loss, and how do we get gradients for these parameters? So for ODE parameters, there's this trick where, so if I want to get the gradient of the loss with respect to the parameters of my ODE, you can always just backprop through this solver. So, these ODE solvers and SDE solvers are written in linear algebra. There's some control flow, but maybe you can kind of gloss over that. That absolutely works for small problems most of the time. There's some caveats, but it has a high memory cost is really the main gotcha. Backprop for many parameters requires you to memorize all the internal state of the whole forward pass, which is going to be a lot if you have to take a lot of steps in your solve and if the latent state is large. So in the ODE setting, you can write down the gradient through Euler's method, and it looks also just like a residual network. And it's just a bunch of Jacobian vector products, which are cheap. They're the same cost as evaluating this function. And then when you take the infinitesimal limit, you end up with an ODE. So you can write the gradients, all the gradients you need as just another ODE solve. This one actually runs backwards in time from the final state. And the cool thing about that is that because ODEs are reversible, you don't have to store all the internal operations. So you can, if everything is well conditioned enough, you can have constant memory gradients where you solve the system forwards, get your loss, and then solve it backwards. And you end up reconstructing all the intermediate variables that you need to compute those Jacobian vector products. And one nice thing is that if you wrote an ODE solver that only runs forwards, you can turn it into one that runs backwards by just sticking some negative signs into the dynamics function. Okay, so obviously, as an academic, I like to squeeze all the juice out of every trick that I find. You know, all that ODE integral stuff was done in the 50s, like, and the gradients and stuff. We just put it into PyTorch and like cleaned it up. So I thought, okay, we need to do this for SDEs. And it's okay, this is going to be surprising. You guys probably shouldn't take my word for this, that in 2019, like there was no like equivalent set of equations for like running the SDE backwards to get the gradients in this like constant memory time. And Belinda Sen and Maxime Roginski, these are like cranky probabilist people, right? They will tell you that your measure theory is like, you know, insufficiently rigorous. They tried to write down this and they worked out forward mode and then couldn't work out reverse mode. And there's like this paper, you can read this. I do want to mention, there's a group at Oxford, Terry Lyons and Patrick Keeger, who are doing a totally different formulation of SDEs that's like, I think kind of nicely refactors things. It's called rough path theory, but we can talk about that later. Anyway, so there's like this technical contribution that like we made, which is, I think, hilariously dumb, but it still had to be made, which is, what does it mean to run an SDE backwards? And there's things called backwards SDEs. There's like all these weird exotic things that aren't actually about running the dynamics backwards. I just guessed. I was like, well, why don't we just, you know, slap some more negative signs on this extra function that we have. And there's these two ways to set up the integrals. One of them is the Trutanovich form, which is like sort of time reversible. And then I coded it up and it worked. Sorry, I'll show you the animation. So we want to sample an entire Brownian motion first, then integrate forwards, then start at the end and recover the exact strong solution pointwise backwards, right? And that shouldn't seem very exotic, but it somehow was. I went to a probabilist at U of T, Leonard Wong, and he was like, what does it mean? Like, you've already sampled this what's filtration forwards. So if you like start at the end and then like sample the same variables, like everything's degenerate distributions, is like divide by zero. Like, what does that even mean? And I was like, but it gets the right answer. So there's something wrong with your formulation. And then him and this amazing undergrad, Joy Chen Lee, sat down for a month and like actually realized that you can write things like this. And Kunita, who's one of the original SDE people, had been writing about similar things. So anyway, it's kind of trivial, but now we know officially how to run SDEs backwards, and we can prove that they converge pointwise and stuff like that. Okay, now this is the more interesting part. Even for someone who doesn't want to use these, and someone who's working on GPs, how do we sample an entire Brownian motion function? And there's actually been some related work, I think, coming out of CBL about this, but I think this is a very different approach. First, I want to mention, so there's the reparameterization trick was like a huge deal in machine learning in like 2013. But SDE people had already actually done this when they made the foundations of their field. They already take all the noise in their whole, you know, processes and reparameterize it into a Brownian motion that has no parameters. So that's cool. I thought we were going to have to introduce the infinite dimensional reparameterization trick, but no, they already did it. Now, how do we sample an entire Brownian motion that we can evaluate anywhere, again with constant memory? Right. So what people normally do is they just store, like there were people who ran adaptive solvers forwards and backwards for different things, and they just stored all the, they just sampled it like forward in time, and then they filled in the gaps on the reverse pass, but then that has linear memory cost. So here's our answer. it turns out that when you're sampling a Brownian motion, there's a way you can do it that looks kind of like binary search, where first you sample the first time, then condition on that, the last time is marginally Gaussian, so you can sample that. And now everything in between is a Brownian bridge, which just means a Brownian motion conditioned on its endpoints. And everything here is marginally Gaussian as well. So I'm showing the mean and variance. So, so what people did sometimes is they built this tree where they say, okay, I will sample the middle. And then if I'm trying to evaluate this Brownian motion at some time tq, I'll just keep bisecting this Brownian bridge over and over until I get close enough. And I converge exponentially quick. So I certainly don't need more than 64 bisections before I've maxed out my numerical precision. And then they would store this whole tree. And then our innovation was just to say, well, you don't actually even have to store this tree. You can reconstruct it as necessary if you just make your random number generator always just initialize it to something that corresponds to which node on the tree you're in. And that's actually really straightforward to do. You can just like hash like left, right, right, and hash that all together. And then that's your random seed. So the point is, you have to choose a seed at the top, and then that determines the entire trajectory of this Brownian motion at every point. And I can query it anywhere with constant memory costs and this like sort of logarithmic time costs in the precision by just going down these branches. It's in like a binary search. So now I can write this little function that takes a seed and a query time, and it doesn't have to store anything. It's not a data structure. It's just a little function. And that's my deterministic sample from a Brownian motion. And I can just pass that little function around for everywhere. And so now old SDE solvers had all this constant like complicated memory management randomness management, where they would have to like sample forwards in time. But then if they rejected a step, they had to like remember the randomness that they previously chose and stuff. We don't have to do any of that. We just have a function that we can query like a normal function. Okay, any questions about this virtual Brownian tree? Okay, cool. And I'm pretty sure you can do like variants of this if you have GPs with like a single input dimension. Like Simo Sarka characterized the case of like GPs in which you can do like linear time inference. I think you can also have slightly more interesting kernels than Brownian motion and still make something like this trick work. I haven't worked out the details though.
So, sorry, can I ask a clarifying question? So is the reason you need this just because you're using an adaptive solver?
No, I mean, it helps. It's even better because I have an adaptive solver, but it's because I want to have constant memory gradients. So if I wanted to reconstruct my reverse trajectory, I have to know what the noise was on the forward pass. So I just don't, even if I had like fixed time steps, I would have to store what the noise was at every time step.
Oh, okay, sorry, that makes sense again. All right, thanks.
Great, thanks for the question.
One more clarification question on this. So I think the key requirement for having this tree is because in the backward pass, the points at which you will be evaluating are going to be different from the ones at the forward pass, no?
Well, that makes it even more important to have this tree, but no, as I was just saying, the key thing is I don't want to store any of the randomness from the forward pass, just because that would take more memory. Yeah, there are like reversible random number generators that would let you do that. Actually, I think.
I mean, I was thinking of just using, for example, the time points as the random seed.
Yeah, you're right. You could do that, and then you could just subtract the local Brownian motion. So yeah, if you had fixed time intervals, you wouldn't need this Brownian tree. So you're right. So this is, in that sense, you're right. It's this more flexible and lets you query anywhere you want.
Yes.
Cool. Okay. So, so putting it all together. So there was this algorithm for the adjoint sensitivity where we define a new dynamics function that runs backwards in time and gives you all the gradients. So now, this is like 50 years old or 70 or who knows what. And then this is like 1 year old. The version for SDEs, it just looks like you copy the thing for ODEs and add the same thing again for the noise. And you have to have a few copies of the noise floating around. But the point is now, if I run an SDE integral forward with a fixed Brownian motion, I can now run another one backwards to give me all my gradients, constant time, adaptive solvers everywhere. Okay, woohoo. And so just to, again, like talk about, to just drive the point home of why we're doing this, if you talk to the Julia guys, they're like, oh yeah, well, why do we need all, okay, Christopher Kakas, he's got, was like a little dismissive. He's like, but we'll just do forward mode. Like, it's fine. What are you gonna fit, like 1 million parameters? We only need like a few hundred for most physical applications. And that's totally fair. So if you only have a few tens or hundreds of parameters, you can get your gradients by going forward, doing forward mode, which has constant memory cost. But you have to run a forward pass for every single parameter in your model. So that's works for like, yeah, only like 100 parameters. If you backprop through the solver, that is like, has a good time cost. You only have to do it once, but you have to store everything in between. And now we have this nice thing. We have constant memory cost. We have this little logarithmic factor because of the Brownian tree, but that's in practice, that's like a very, there's no neural networks or anything in there. So it's like a very small factor. Okay, so now we can fit big SDE models by gradient descent. And so here's our, oh yeah, and so the last part is just how do we write down a loss, right? We can't just fit the SDE to data directly because then we will overfit and turn off all the randomness. Or rather, like, you know, anytime I'm fitting a random variable to a deterministic like data set, unless you do something like Bayesian inference, the optimal solution is going to have 0 uncertainty. So we just have to, we're going to set up this thing like a variational autoencoder again. And so now here's our graphical models. This is actually the same graphical model as the latent ODE, where we have a random initial state and then a deterministic dynamics. But the new part is this W. This is our sample from our Brownian motion. So all the noise is, this is like an infinite dimensional VAE, right? Normally this would be like the noise in our, like the Z in our VAE. Now it's a Brownian motion. And again, we can have arbitrary likelihoods at arbitrary times, no problem. And so, and as Miguel was saying, oh, well, we have to make a recognition model that somehow like looks at all the data and gives us the parameters of some posterior. So I'm going to talk about how we characterize the posterior now. That's the like last missing piece. So, to fit this model to data, we have to write down a prior SDE. So F theta is just the prior dynamics or prior drift. Sigma theta is the prior diffusion, and we have to have a likelihood. And now the like missing part is how do I define the approximate posterior? That seems weird, right? Okay, I had a SDE prior, I conditioned it on some weird likelihoods. What does my posterior look like? And this is a huge problem like for Gaussian processes, right? We start with a Gaussian process prior and we put like a classification likelihood, and suddenly we have something that's not a Gaussian process anymore. So we can't just, you know, we don't know what the posterior even looks like. This is the coolest thing about SDEs as a model class is that you can use another SDE to parameterize the approximate posterior. And that is a family of functions that I don't want to say contains the true posterior, but can get you arbitrarily close to the true posterior. I think actually under mild conditions, it does contain the true posterior, but I don't want to stake my mathematical reputation on it. So what inference in this approximate inference looks like in this model is we look at the data and we come up with the parameters of a new drift function that tells us how things move around in our approximate posterior. So SDE prior, SDE approximate posterior, and I think an actual SDE true posterior. So that's where this is like a way, way, way cooler model class than GPs, because we don't leave the class of SDEs when we do one of these conditionings or even like marginal transforms. We stay in the same model class. Okay, and I guess this is the very last piece. What does the KL divergence look like? What does the elbow look like? So again, I have a prior SDE, a posterior SDE. The elbow looks like the evidence lower bound on the marginal likelihood looks like we have our likelihood. That's the standard likelihood of the data given the latent trajectory. And then we have an integral through time of the difference between the prior drifts and the posterior drifts, normalized by the diffusion. So this looks like the KL between two Gaussians, basically, like if these are the means and this is the standard deviation. So we just sort of go along through time. We have to, this expectation is over samples from the approximate posterior. So we sample a trajectory from our approximate posterior and we say everywhere, how different are we from the prior? And then the more different we are, the larger the KL divergence.
May I just ask a quick question? Sorry,
yes.
Hi David, thanks. Is it, so it is important here that you have sigma theta on both the prior and the posterior?
Yes.
Because is it because of this change of measure that they need to have absolute continuity and this kind of argument?
I would say yes. So that's, this might seem like a huge limitation. So that's one thing I hadn't mentioned is like, oh, the approximate posterior has to share the drift with the prior. And yeah, so the basic idea is that the KL divergence between SDEs that have different drifts is always infinite. And there's a similar thing in GPs, actually. If I have like the KL between two GPs with different kernels, like even like if one is the prior and one is the posterior, it's always going to be infinite if I have different covariance functions. So it's the same sort of thing here. And this might seem like a huge limitation, but it's not. And I will show, I'll demonstrate on the next slide or next two slides that you can make this approximate posterior do whatever you want, no matter what this drift function or this diffusion function is, like informally.
Okay, but you can still learn it, this sigma theta.
Yeah, so these thetas are kind of like the kernel hyperparameters because they're going to tell you what the prior should be.
Okay.
So this then means you always have to have a learnable prior.
Sorry, my internet cut out for a second there.
So this means you always must be learning your prior?
You don't always have to. It's just like a GP. If I have a great prior from somewhere, I don't have to update it, but usually you want to because you don't have a good prior. So, you know, and if I really wanted to, I could put a prior on these thetas or whatever. But the point is, just like in GPs, the analogous quantity in GPs, this is the kernel, and then this is just helping us do approximate inference. And I guess I shouldn't say just because like doing approximate inference is like the hard part. So cool. So now training this whole thing looks like we just you know, sample a trajectory from Q and evaluate this thing with another SDE integral. We can actually do it a lot, like all together in just one big SDE integral, and then get gradients through the whole thing. And it's just like training a VAE again, except we have this called the SDE int inside of it. Okay. So that's the end of the hard math. Now we just get to play around with this new model class. So here's me fitting an SDE just in one dimension. This is toy. This all works in like arbitrary dimension vectors, but so this is fun. So here I'm showing you an SDE, which is an OU prior. So you guys remember the OU prior? It's like the drift is just negative of the state. So that's pointing us back towards zero. That these gray things, that's the prior drift. And we have just a unit diffusion everywhere. And so here's some samples from the OU prior, right? This is just a GP. It's also an SDE. Okay, and then we can, now let's put a Laplace likelihood on this data, right? And it's like, oh, Laplace, but now you're not gonna have a GP posterior anymore. It's like, yeah, that's okay, because now we have a new way to do approximate inference. So now I'm going to maximize that elbow, maximize that elbow. And all that I'm doing, the only thing that's changing here is this little neural network that parameterizes these gray arrows. And they're going to steer all the mass to be near the data. And of course, the KL is going to want to make us be uncertain where we're away from the data. So we keep our uncertainty away from the data. So this is a sensible looking posterior. But now it's not a Gaussian process posterior. Cool. And here's us, just to show that it works in more dimensions, some Mocap data. So the data is like these XYZ positions of all these little dots through time. And this is a sample from posterior that's learned, we learned a joint prior over like a whole bunch of trajectories. And so it looks like walking, right? And the point is this is like a very early experiment. It had 11,000 parameters, which is of course nothing by neural network standards, but it's like mind blowing to SDE people who usually fit like 1 or like 3 parameters. Okay, so that's like the practical demo. Any questions about what was going on in this whole setup?
Hi, David. I was wondering, just on the parameterization of the approximate posterior, well, the posterior SDE. I noticed the drift term didn't depend on time; it was just a function of the state.
Oh, I mean, that was just me trying to save symbols, probably. Like you can make everything depend on time. Yeah, good.
Oh,
good,
okay.
good catch. Sorry about that.
I'm sorry. Just.
Yeah, everything here can depend on time, and these are getting to be pretty big equations. So great. Oh man. Yes.
So if we assume we are dealing with a regular spaced time index for a moment, then could you give some intuitions on the difference between learning ODE model over learning the latent dynamics directly using neural network?
Yeah, good question. So maybe you could say, is there any point in doing this if I have regularly spaced time data? And that's fair because this example does have regularly spaced time. And the answer is not really. And it's actually slower because now I have these adaptive solvers. However, and there was a bunch of people who were applying neural ODEs to like video, and I was saying like, don't waste your time. If unless you want to answer queries like in between points, so people could like interpolate between video frames with ODEs, and that makes sense. But otherwise, I wouldn't use it for regularly sampled time series. With the exception, the thing I'm going to talk about at the end here is what if I want to have multiscale dynamics? So there's a few papers with these like clockwork RNNs or RNNs that like have like a slow moving variable that only updates every like 10 frames, and then like faster ones that update every frame. The problem is like, how do you choose how often to update? That's like this funny hyperparameter. Sometimes people try to do like crazy stuff with discrete gradients, and in the continuous time setting, you can actually learn a hierarchy of timescales with gradients that are like, the gradients will let you learn the sort of slowness of the higher levels jointly at training time instead of as a hyperparameter or with some horrible discrete gradient estimator.
Cool, that's very helpful, thanks.
Great. Okay, so yeah, so then I'm saying, look, come play with me in this new model class. We have torch code, stick whatever you want on the likelihoods, train everything with SVI. You get to use adaptive solvers. You can even use higher order solvers like Milstein. That's like order 1.5, which is not actually that high, but that's about as good as you can get in SDE land. Okay, and now this is like the CBL special slide because you guys will probably be able to help me think about this. Yeah, so I'm saying GPs, they have mean and covariance functions. SDEs have these drift and diffusion functions. Neural processes, I don't really know that much about neural processes, to be honest. It's like, okay, I guess you define the sort of inductive bias by the encoder and decoder architectures, maybe. GPs, they drove me nuts. My whole thesis was on how do I like fit more things into the GP framework, but anything you do to them pretty much breaks them. Like for instance, if I just want to take the pointwise exponential of a function drawn from a GP, it's not a GP. But if I do that to an SDE, that's still an SDE. And in fact, there's a closed form for like how to transform the drift and diffusion functions to get like any parametric transformation pointwise. GPs will let you do like spatial fields and whatever, but it's not really clear that that makes sense for SDEs. Maybe then you have like stochastic PDEs, but then that's really slow. I don't know, neural processes, what can you say about them? I don't know if there's anything to say. I think they can handle multi-D input about as sensibly as GPs. Is any NP aficionado here? I know we have some of the original NP people here. Want to weigh in on what they see the relationship between these two models is? Okay, well, at the end, if you guys think of something, okay. So then just like, I'm gonna blast through a couple of like things we've done with these models. So one is SVI is annoying because it bounces around. It has this, it adds gradient variance to your training. And even if you have the true posterior exactly, and your approximate posterior is exactly the same, it'll still just have this gradient noise and bounce around forever. It turns out that there's an alternate way to write the a still unbiased gradient estimator for stochastic differential inference that has gradient variance that goes to 0 as you approach the true posterior. And we had this paper called Sticking the Landing. But the thing is that this was kind of niche. Like, no one actually used it because no one had posteriors that approached, or no one had approximate posteriors that approached the true posterior in general, unless you use like a normalizing flow or some exotic thing, but that's sort of too expensive. But in this model class, our approximate posterior is like arbitrarily flexible. Oh yeah, I forgot to explain why it doesn't matter that the diffusion is shared, but the point is I have an a really rich approximate posterior class. So here is us, here's me, and again, it's like a toy regression demo, fitting a prior to like this Cauchy likelihood data, and ending up with a bimodal approximate posterior. So I have, like, I should have shown the drift function, but basically it's like pushing the data up here and down here, or pushing the trajectories down here and up here. So without any mixtures or increasing the number of parameters or whatever, it's already natively can support like a whole bunch of modes. And I mean, you need to add more parameters to your neural network to have more complicated approximate posterior. But the point is, if I just make my posterior drifts rich enough, I can approach the true posterior as closely as I want. And we extended this like sticking the landing idea to SDEs. And now we have this gradient estimator whose gradient goes like arbitrarily, or whose variance goes arbitrarily small. So that's fun, right? We don't have to ask like, well, maybe we could have like a mixture of Gaussians or make our Gaussian full rank or whatever. Everything's already totally correlated and full rank or whatever. The price you pay is that the SDE solver might take a lot of steps if you have a really complicated approximate posterior. Okay, any questions about that? Cool. Right, so the takeaway is just we have this new awesome model class, start with an RNN. We have code available. And then someone still needs to do this whole thing again for like Levy processes, like jump processes. And also, like, I think there's a whole bunch of applications. People just started applying this stuff to like finance. And I'm just going to talk about like very last 3 minutes, 2 different things we did. So one is, oh yeah, when I was a PhD student at Cambridge, I remember walking down the hall and being like, oh man, I should develop an infinitely deep neural network. That would really impress Zubin. But then being like, I have no idea what that could be. It would have to be some sort of weird limit. And then turned out like other people than me before neural ODEs made the connection between ODEs and neural networks. And it's like, yeah, that is like infinite dimensional neural network. It's sort of non-parametric in a sense. When we have SDEs, we can say, okay, what if there's a different set of weights at every infinitesimal layer? Then we have a prior on weights that could be like a SDE, and we can have an approximate posterior on weights that's also an SDE. So sorry to gloss over this, but we have this like joint SDE for the weights of our Bayesian neural network. And here T refers to the depth as we're going down the layers of our neural network. And then another sort of ODE for the hidden unit activations. So, you know, yet another Bayesian neural network, and it fits, you know, toy problems and it fits data fine. The reason that this is a little bit refreshing is because now we have a awesome class of approximate posteriors that again contains the true posterior or like arbitrarily closely. So we don't have to separately worry about how expressive our prior is and how expressive our approximate posterior is. And we can again like trade off between we can choose the error tolerance of our solver to make the approximation sort of faster to run but less accurate if we want. So that's like another knob we have to tune. So okay, and then the very, very last thing I want to mention is that there's a connection. I haven't formalized it exactly, but I think it's pretty straightforward, between multiscale hidden Markov models and SDEs. So I claim informally that the infinitesimal limit of this hidden Markov model architecture corresponds to this SDE architecture. And this is what I was saying to Hong before, is it would be awesome if we could have like multi-scale SDEs. The reason why this is cool is if I want to make predictions about some really fine-grained process, like months ahead. So here's an example. I'm modeling infant heartbeats. So they like beat like, once a second or something. And I know that like if I measure a baby's heartbeat, probably in a month, it'll be a lot slower because the baby's going to be bigger. And so maybe the baby's overall size is like some very smooth SDE that's like very easy. You can take steps that are like super long and very cheap. But if I wanted to reason jointly about the baby's heartbeat on day 1 and day 100, naively, I would have to run an SDE solver for like 100 days at this like very fine granularity, and it would take forever. But if I have a multiscale SDE, I can condition on the data on day 1, get a posterior over the like slow variable, extrapolate that forward in time, and then now again reason about the data or the fast-moving process 100 days later without ever having to reason about like all the stuff in between. That's just going to mix back to the prior or like the conditional prior. So it's all very like sketchy. And here's like literal sketches of like me talking about, using the multiple scales to avoid having to integrate in between. But I think you can do this, and just like in a GP, we can marginalize out all the GP that's away from the data. We also can do this in these multiscale SDEs. I think it's a little bit hand wavy at this point. So I really want to do that and add like extra auxiliary variables to the approximate posterior, just like in physics, where we have like pressure and temperature that are like these made up things that help us reason about the dynamics of like these like Planck scale systems. I think we can do that all in this framework, jointly train everything with marginal likelihood. And here's something we did in the ODE setting is I was saying, oh, it might get really slow, right? If you have complicated dynamics, everything's going to slow to a crawl. You can also tell your training, you need to make these dynamics easy for a solver to integrate. And so you can choose the trade-off is like, how much accuracy am I willing to pay for how much sort of SDE integration time? We haven't done this yet, but I think that's something you can do to control the time cost of all this, which is really the reason why this is annoying to work with, is because these SDE solvers are like kind of slow, especially because we don't have good software for it yet. Okay, so I'm gonna have to skip over like related work, sorry guys. And there's a new programming language that I'm working on to help deal with this stuff. But so Zhuochen Li did a lot of this measure theory. He coded up all the SDE solvers. Winnie Zhu did all the Bayesian neural network stuff. Leonard Wang did all the measure theory stuff. And Ricky and Yulia did almost all the latent ODE stuff. So thank you very much. It's been an absolute pleasure.
Thank you very much, David. I think I'm going to stop the recording. Then we can do a few questions and then have a nice discussion.
Wonderful.